Hit record. There we go. So I put a link on Moodle to the YouTube site that's got the lectures from last week so far. So take a look at that at some time, and if there's any problem with that link, let me know. When I clicked on it, it seemed to work fine. So if you have any problems, just let me know. Okay, so today we're going to be talking about the building envelope. Before we start, I wanted to go quickly over the assignment from last Friday that you guys all turned in. Everyone did really well, not a lot of confusion. One thing or two questions I wanted to go over were, actually it was only one, and again it was going back to the bin hours in 1 week, which we briefly touched on last Friday also. Just don't get confused about the 1 week, which is 7 days at 24 hours, which is 168, and it's not the full year. It was purposely a little tricky to make you think and read the words. But almost everyone got that right. And everyone who filled it, did the assignment, got full credit. So are there any questions about the assignment? Nope. Okay. Then I'm going to jump straight into the building envelope. Not this envelope, but this envelope. The key thing to remember about the building envelope is that it is the skin that is a continuous surface that is protecting the heated and cooled environment from the elements. And that could be from the sky or from the ground. So therefore, in this case, in this example, the basement here is technically part of the building envelope because it is assumed to be heated and cooled because this is within the envelope. If we were not heating and cooling the basement, then this red line would go straight across. So if the basement were not part of the envelope, as in not heated or cooled, the envelope would stop right there. In this case, the attic space is not being heated and cooled, and so therefore it is not included in the building envelope, but the interior 2-story space is. Get rid of my line, okay. Okay, the building envelope is the most important part of the building for heating and cooling loads. It encloses all of the conditioned space, and it is what creates that separation from the interior and the exterior environments. And again, that can be air or it can be the ground. And it also protects the building from the climate and weather conditions. It needs to be, it's also, so in terms of weather, it's protecting the building from moisture, air, heat, and cold. It's really important. As practicing architects, a lot of time will be spent controlling moisture and making sure that moisture is not penetrating into your building. So what does that mean? It's the most important part of the building. The building envelope is the point at which heat is either lost or gained into the building. And this is through our 3 methods of heat transfer, which we went over last week, which are either conduction, convection, or radiation. And in terms of our solar geometry and our building mass, the solar radiation that hits the building envelope is going to be either reflected, absorbed, or transmitted. Reflected back to the atmosphere, absorbed into the envelope skin, or transmitted through transparent surfaces such as glazing into the interior of the building. There's a bunch of terminology that is really important to understand for looking at the performance of our building envelopes. There's the U value, which is the conductance value, the R value, which is the resistance value. And remember that the U value and the R value are direct inverses from each other. So U equals 1 over R, or R equals 1 over U. Key thing for looking at glazing is going to be the solar heat gain coefficient. Different types of radiation that are affecting the building are the direct solar radiation or the diffuse solar radiation. And we're going to be going through all of these terms. So this is just to spit them out there right here at the front, and then we'll go through and talk about each one of these. So there's 2 different types of radiation, direct and diffuse. There's the solar heat gain, which is not to be confused with the solar heat gain factor. Then there's also a shading coefficient and the thermal lag or the time lag factor. Okay, so right now there's 3 terms here that are all fairly similar, and we're going to go over these. But solar heat gain coefficient, this applies to glazing. Then solar heat gain, that applies to the overall envelope. And then there's the solar heat gain factor, which is the least important of those terms, but don't get that one confused with the solar heat gain coefficient. Okay, so our U value, this is conductance. So we talked about this briefly last week. The U value is used as the letter C in our heat transfer equation. So our heat transfer equals the U value times the area, because it's talking about the surface area, times the temperature differential from the outside to the inside, or from one room to another room, or from one surface to an air surface. It can be, and remember that heat is going to want to try and be at equilibrium. So if you have a space that's warm and a space that's cold, they're both going to try and equalize themselves, and the heat is going to transfer from hot to cold until it reaches equilibrium. And once again, to reiterate that the conductance, or the U value, is the units are BTUs per hour square foot degree Fahrenheit. So BTU is our heat load over a period of time, that's the hours, over the area, and then degree Fahrenheit, that is the temperature differential. The R value, the resistance, is the inverse, or the exact opposite of the U value, and that is going to be what is resisting heat transfer through either a surface, a material, or a wall assembly, roof assembly, floor assembly. Excuse me. Okay, and then solar heat gain coefficient. These terms, U value, R value, solar heat gain coefficient, these are all factors that are going to affect what we call the Title 24 calculations, which are our energy compliance documents that are performed as part of our building permit set to meet the state energy code requirements. Engineers tend to refer to them as the compliance documents. Architects just tend to just say the Title 24, Title 24. Title 24 is just the code section that covers actually more than just the energy code, but it's just become shorthand in the industry that when you hear Title 24, it's typically referring to the energy code requirements. I was going to take this out because all the, yeah, don't worry about this one. I forgot. It's all in not imperial measurements, so I don't want to confuse you guys. Okay, R value. Oops. No, wrong slide. R value. So again, this is the resistance. It is measuring the thermal resistance of heat transferring. Again, it's the inverse. It's the opposite of conductance. The higher the number, the better. For example, with our insulation, the higher the R value, the more it is going to resist the heat transfer. Typical numbers for wall assemblies are R11. That's the size of a bat that fits into a 2x4 wall. In fiberglass bat insulation. R19. That's the size that fits into a 2x6 wall, and R30 is a typical roof assembly value. We're really lucky here in San Diego, even with our stringent energy codes for California, our roof insulation requirements are not as high as they are in much colder climates. They can get to be, above 40 or 50 for requirements, or to give you just a good performing building. So keep in mind that insulation is key, or insulation is sexy. Just keep you guys on your toes here. You guys do know who the Pink Panther is, right? I mean, okay, well, he typically was the mascot for the pink insulation for a long time. I don't know. I don't watch TV. I don't watch commercials anymore because all we have is Netflix or Amazon Prime or something. So I'm a little out of date on commercials. Okay. These are just a couple of examples to walk through how a wall assembly you can start will start to be calculated for its R value. This is what the mechanical engineer does as part of his energy modeling for those Title 24 performance calculations, compliance documents is what I meant to say. So let me get my little drawing tool here. So starting at the top, this is just a straightforward 12-inch CMU concrete masonry unit block wall, assuming to be fully grouted. That means that there's no, the hollow cells that are inside are grouted with cement or concrete. So simple wall, but it has 3 different R values or R factors that you have to add up to look at the entire assembly of the wall. Remember how we talked about air you can't forget about the air on either side of the wall. So this is considered to be an exterior wall, and it is looking at a wind factor on the outside surface of the wall. That's my little circle. So on the outside surface, there is a very thin layer of air that will stick to this wall surface with a minimal R value, because wind is considered to be moving across the surface. Then you have the R value for just the solid thickness of the concrete, and that's this value right here. Then the inside surface of the air, which does not have wind moving across it, has a slightly larger R factor than the outside, which has that wind factor. So this is approximately trying to draw in relation to the value. Okay, so you add up all of those different factors, and these are found readily in different charts. Don't think we have any here today, but on Friday, whoops, I can't. On Friday, when we do a couple load calculations, we'll start looking at some of those. Yeah, we're not getting in there today. Okay, so okay, very simple wall construction, very straightforward. There's no insulation on this. Okay, so now let's assume that we're going to add some drywall to the inside of this CMU wall assembly. We still have our outside wind factor, our concrete lock factor. Then here, what is this? Airspace. I'm going to assume this is the stud wall here, and it looks like it's drawn more like a metal stud, but this is a 4-inch airspace. So we get this factor for that air, and then 2 layers of drywall and the inside air surface. When looking at the performance of this overall wall, even with the stud spaced 16 inches on center, they're still considered an airspace for the calculation of just the assembly. Okay, so adding all
so
of
those studs just get left out of the diagrammatic drawing?
I have a line in here somewhere later. Whoops. Let's see. It's not that they get left out, it's that their area is not significant enough to affect the thickness of the wall. Now, because most studs are 16 inches on center for a wall, or a ceiling, or 24 for a roof, it's not that they get left out, it's just that they're negligible in the overall surface area of the wall. So if you're looking at like a 10 by 10 square foot wall with this many layers in it, the metal stud or the wood stud here, that distance, and when you add up all those studs, is negligible in the overall performance. Now, the engineers will have, they won't sit here every time they do a wall for every single wall in your building. They'll say, okay, what's your assembly? And they'll have a chart of what these values are given for a certain wall type with a certain insulation value. So I honestly can't say if they actually take those studs into consideration for those chart values that they use, but for us as architects, right now, all I want you to concentrate is thinking about all the different surfaces and how they add up, and that the studs pretty much are providing an airspace. And now moving on to the same wall, but putting in that insulation within that stud bay. So 4 inches of fiberglass. If you recall, when we were looking at our values up here, R11, resistance value of 11 is the typical 3.5 inch stud resistance value. That is the resistance value for a typical 2x4 stud with fiberglass batt insulation. The key thing here is to notice how much of resistance this is adding to this overall construction. So, oops. Oops. That's not what I wanted. Go back there. Back to my circle. I'm moving this over here. There we go. So we have an R value of 15 overall for this wall assembly when we add in 4 inches of insulation. And the majority of that performance of that R value is all coming from the insulation, compared to 5 when it's just an airspace, or 3 when there's no airspace and no insulation. And again, so the reason air is the #1 insulating material, and the reason the batt insulation is creating such a high performance for that material is it's adding a lot of surface area and very small air volumes, so that because the air is hitting all of those surface areas and not going straight through the one giant airspace. Remember, so I'm talking about insulation last week. Smaller pockets of air to a large surface volume is what creates that resistance factor, because the heat is getting caught between all those little tiny surfaces around the bubbles of the air that are hitting the fiberglass strand insulation. Okay, so these are 3 different wall examples. Erase. Clear. Clear. There we go. Okay, this is a roof assembly with an outside roofing surface, built up roof with 3/4 inch of styrofoam insulation, which let's jump down there and see 3/4 of an inch of styrofoam. That gets us just over 3 on R3. We have concrete, wood fiber board, which is also giving us a fair amount of insulation value. Straight up empty airspace, very, very low insulation value for that 16 inches. We've got steel studs and furring channels, so that's those layers.
And can the increase of the R rate, the effectiveness of the R rate go up and up and up, or is there a point where it reaches like a nominal value?
It's pretty direct, and yes, it can go up and up and up, but you're going to get to a point where your thicknesses get so thick. Economically, we tend to, or architects tend to go with that sweet spot where it's thick enough to give the performance that we want, that the size of the equipment for the heating and cooling load is not overwhelming. Couple of examples though about that. And we have, is anyone familiar with an ICU product, insulated concrete for ICF, insulated concrete form? I heard one yes. Okay, so that's an example of a product that it's a manufactured product that adds rigid insulation to the exterior surfaces of concrete masonry units. So that's adding some insulation on there. So it's giving you a better performance value. Another thing, straw bale construction, where you're using bales of hay or straw, excuse me, that are anywhere from 18, 24, could be 36 inches deep. I think usually it's about 24. Those are great at insulation because there's a lot of air entrapped in there, and there's also a lot of surface area. So it's a very, very high performing insulating wall assembly, but you're at 2 feet thick. So that's going to take a lot of footprint. And typically you're going to need larger land area for the bigger footprint. It makes your envelope a little bit bigger, which makes some of your material costs go up. So there's all of these different factors that come into play on where is that sweet spot of how much insulation to use and how thick your assembly is going to get in trade-off for your performance of your building. I believe I briefly mentioned the passive house movement at one of our classes. It started in Germany, and it is promoting an incredibly high-performing envelope. So what they require is, it's actually a double stud construction wall with insulation in both studs, and then also an airspace in between, which is acting as a thermal break. We haven't gotten into thermal breaks right now, but what it does is it prevents conductance from the outside to the inside, because there's an air gap in there. So passive house has very thick constructed wall assemblies in order to have a very high performing envelope so that the loads on the building are as low as possible. They have other standards about infiltration and then also ventilation, and there's other factors that they look at too. But one of their biggest ones is very, very high performing walls. There's a couple of buildings. I worked on one building here in San Diego that got passive house certification. It's out in Ramona, where the summer and winter temperatures are a lot more extreme than they are, say, downtown San Diego. Ramona can get really, really hot in the summer. Not as cold in the winter, not like northern climates, but it really helps. In their case, in Ramona, it was for reducing the cooling loads, because they have more cooling and more requirement for cooling in the summer. So it's passive house. Okay, it's like, oh, another example. I actually worked on a house on Bankers Hill here in San Diego that was right on the canyon there that comes up along First, Second. I forget the name of the canyon. Anyway, and so it was a 4-story house there, tall and skinny, and had a lot of west-facing glazing and a lot of surface area. And their mechanical system was ridiculously large for their cooling load. And so we looked at increasing the wall thickness I can't remember if it went from 2x6 to 2x8 or 2x10 maybe, I don't remember, but adding in more insulation in their walls where they had them and going with a higher performing glazing cut the heating load in half. So it went from like 12 tons of AC down to 5 or 6 tons, which makes a huge difference, not only in the installation cost of the size of the equipment, but in the operational cost, you know, over the lifetime of the building. To keep, so in that case, it was worth it to increase the performance of the walls because it had all of these other beneficial, economically beneficial effects on the design. Okay, so building envelopes. Oops. Yes. Okay, and again, here, this is a roof. So don't forget, there is the come on, mouse. Let's draw. Let's not forget about our air surface on the exterior and our inside surface down here, which is still air.
What is a furring channel?
A furring channel is, so you have a stud, and then to fur is to make something thicker by adding another piece of material. In this case, it's a metal furring stud. Sometimes it's wood to have another surface to attach drywall or another material to. In this case, I would say this could be acting as what's called a resilient channel, which is a type of furring channel. And what that does, it's creating a sound break from transferring sound from the structure, which in this case is the metal stud, the joist, and the concrete above. It creates, because sound transfers through solid materials. And so by creating another airspace there with this gap to alleviate that sound transmission. That's a specific channel for sound is called a resilient channel. Furring can refer to multiple uses of building out your assembly for various purposes. For example, on a block wall, if you want to drywall the inside, but you don't want to build a whole 2x4 wall, you can add 1x or 2x strips of wood at 16 inches on center to be able to attach your drywall to the inside of a block wall, because you don't want to try and put drywall directly up against CMU. You need something to be able to attach it to. You don't want to be attaching drywall with concrete screws to a concrete surface wall. It's much more easy to use a drywall screw into a piece of wood. And then you just have to have the concrete screws for your wood furring into your block wall. Okay, so good question. Things like that will come up too. I'll use a architecture term, you know, if we're talking about roof scuppers or crickets or furring or all these things that I forget that is just part of my terminology now. Please always feel free to ask me. One of the things I really love about architecture is actual construction and knowing how to build things. And I really like sharing that and helping you guys learn all those things too. I would, I've actually got in the other room, we're doing a little bit of construction on my house, and I've got a drywall ripped open concrete block that you can see the wood furring strips on. But maybe I'll take a couple pictures and put them in the next lecture. I don't want to try and deal with walking through the house with the camera or the laptop right this second. Okay. Wall assemblies. Okay, so we talked about insulation and how every material in your assembly has its own specific value, how they all add up together to give you your overall performance for your assembly. So, are there any other questions about that before I move on to talk about glazing? Nope. Okay, I don't hear anything. One of the terms from earlier today I mentioned was the solar heat gain coefficient. This is specifically related to glazing, and it's set by the National Fenestration Rating Council. And every manufacturer of a window has to have performance data on their products in the state of California. So the SHGC is a combination of both transmitted solar radiation and absorbed solar radiation into the glass, and how much of that heat transfer is coming to the interior of your building. It's always going to be a number between 0 and 1. The lower the number, the better performing it is. It means the less solar heat that is coming through. And let's look at some examples. So this is a page from a Pella window, which is a manufacturer, a pretty straightforward double hung window. Here are the performance values for this particular window. We have the U factor, SHGC, and then these are the performance factors that are going to be taking the engineer, mechanical engineer, or your Title 24 consultant will take these factors and plug them into the compliance documents. The thing that you're going to be most interested in, besides the performance of the window, is your visible light transmittant, which is done in a percentage. This tells you how much visible light is coming through your glazing. If you want it to be, this is a window for daylighting, the higher the visible light transmittance, the more daylighting you will get in the space. But it's often a trade-off of your performance for your U factor, which is your conductance, and your solar heat gain coefficient. So for example, this is a clear insulated glass unit. The material between the two pieces of glazing is going to be air. Some windows will have argon in that insulated glass unit because it can give higher performance. So we're looking at this. And this has an advanced low E glazing. So here's a U factor of 0.46. But if you start to put a low E coating on one surface and some argon in the center of your two pieces of glass, the U factor, the conductance, goes down by almost a half. Solar heat gain coefficient goes down even more, a little bit better than a half. The visible light transmittance goes down a little bit. Okay, but now if you started to go look down at like tinted glazing, like a bronze glass, because those are oh so beautiful. Sorry. Your U factor goes down, and so does your visible light transmittance. So there's this is the whole sheet, yeah. So when you're working on your design and you're working with your window specs in conjunction with your mechanical engineer, you're going to have to look at all these different factors and say, well, what do I need my performance to be? But here's where I want my visible light transmittance. But maybe if we go with the low E coating on one surface, that will help rather than having it be bronze glass. So there's all of these different factors that come into play for picking out your windows. So taking our performance values from whatever window we decide to go with, and then this, oops, back to mouse. Here's a page out of Title 24, just some random sheet from some project at some point. They list every single window and the size, which is the area of your window. And then you've got your U factor and your solar heat gain factor. This is going to be your performance criteria for that window as part of your load calculations for your building performance. Oops. Undo. It was. I didn't include a page, but similar to your window compliance documents, you will also have one for each of your wall assemblies, and that's where there will be a column that lists the R value for that wall assembly that the engineer will pull out of a book or a chart somewhere.
Oh, I had it.
Okay, so SHGC.
I don't know what this is here for. Oh, I know.
Okay.
You want to get back up there.
Oh, okay.
Let me just look ahead here a second. Okay. So in addition to just how solar radiation is going to affect our glazing of our envelope, it's going to it's also going to affect our solid surfaces through conductance, where the solar radiation is going to hit one surface. It's going to conduct a certain amount of heat through it, and that material is also going to absorb a certain amount of heat. But let's look at some of these factors here. As you recall from our solar geometry, that the Earth's orbit around the sun is ecliptical, but it's not an exact ellipse around the sun. One of those factors of why our equinox and our solstice days can vary a little bit, that in January, and again, this is northern hemisphere, more solar radiation hits the Earth than in July when the sun is a little bit farther away. And it's not like half or anything, but it's a little bit of a difference here. So that is because of that irregular elliptical path around the sun. BTU, we've talked about this. This is a unit of heat, and the stands for British Thermal Unit. I might have skipped over that before. And its value comes from the amount of heat required to raise 1 pound of water 1 degree Fahrenheit. but that is a specific heat, not a unit of heat transfer, which has the hour added to it. So when you're talking about the actual heat transfer, it's going to be BTUs per hour. And in the rest of the world's metric, that's called a watt. And 1 watt equals approximately 3.412 BTUs per hour. And if you're ever going to try and remember this number, which you don't have to, you can always look it up. But if you're doing a lot of calculations, if you're an engineer, you would probably need to know that. And it drives me crazy. Does anyone see what that number is almost like? What number is it almost?
Pi.
But it's not. It switches the 1 and the 4. So it's really annoying that it's so close, but it's different. Okay. So heat extraction capacity of air conditioning. So when we're talking about BTUs per hour, when we have 12,000 BTUs per hour equals 1 ton of conditioning. That example I gave you about the Banker Hill project, where we went from 12 tons down to 5 or 6 tons of load, that's where this comes from. And it's like 100-year-old terminology that when the first cooling equipment was established, it was basically using ice to create cool air. And so 1 ton is how much ice melts in 1 ton of ice. 1 ton equals 1 ton of ice melting. It's the weight of 1 ton of ice that in 24 hours that melts, that is 12,000 BTUs per hour. So that's how it came about. It's ancient, and now we have weird ass numbers, we have weird numbers like 3.412, whereas the rest of the world talks in watts. We no longer have Ice Builders Association. These days it's ASHRAE, the American Society of Heating, Refrigeration, and Air Conditioning Engineers. Previously it was just American Society of Refrigeration Engineers, but ASHRAE. And you're going to hear references to ASHRAE standard this, ASHRAE standard that, and they all have these numbers. You don't have to worry about that today. That's why we have tons of air conditioning or tons of heating. It all has to go back to melting ice. Okay, so that solar radiation that's hitting the Earth, which is 444 BTUs per hours per square foot in January. Different things happen to that once it hits the atmosphere. We get direct solar radiation and we get diffuse solar radiation. And I do have some little pictures of this. And then we also have reflected solar radiation from surfaces. We were talking about heat island effect a week or so ago. That's where the reflected solar radiation really comes into effect. Okay, so let's look at those. So we have our albedo. That is the diffuse reflection of solar radiation from the surrounding terrain. So where the solar radiation is hitting our Earth's surface, be it concrete, dirt, water, or building, there's going to be diffuse reflection from that, and that is what the albedo is. The whiter it is, better. It tends to be better performing. it's a reflection coefficient, so it's going to be like a percentage, so the value is always going to be less than 1. It comes from Latin, meaning weight. And the measurement is the
You said weight?
white.
It comes from white.
White, Latin for white or whiteness. Albedo equals whiteness, or albus equals white. Any Harry Potter fans out there? Albus Dumbledore, white magician, maybe a reference to Tolkien, perhaps, maybe. Okay, so it's a ratio of the radiation reflected from the surface to the incident radiation. Okay, that's probably not very clear. I'm going to skip ahead to here. No, I'm going to wait for that. We'll come back to the incident of, I think that's supposed to be incident of radiation because it's an angle. So the lower the value, the more it absorbs, which means we get a higher heating. So the closer the value to 1, the better performing it is. This is the opposite of our solar heat gain coefficient for our windows. The lower the value there, the better. With albedo, the higher the value, the better, because it means it's reflecting more. One thing to consider, though, is in more urban areas, if you are trying to have really high albedo values, you can end up actually affecting your neighbors by reflecting so much light that it's going through adjacent buildings' fenestration, so it's coming up from the ground. So just keep that in mind. Okay.
That
So,
kind of reminds me, sorry, of the, you know, that Disney Hall concert
yes.
in LA, because it reflects so
Mhm.
much. There was so much, I mean, it was good for the people inside the building.
Right.
There was so much complaint from the surrounding.
From the surrounding buildings.
neighbors.
And I believe right next to that is the LA Department of Water and Power building, which is a super cool 60s modernist building that is like all single glazing. And I believe I remember hearing that high reflectance of the Disney Concert Hall was actually increasing the air conditioning loads in some of the buildings around there. And wouldn't it surprise me for the LA Department of Water and Power building, because the building is historic now, but their glazing is so poorly performing because it's single glazed.
Yeah.
Yeah, exactly. So things like this, sometimes you don't realize them, no matter how good a designer the world thinks you are. Okay. I like this diagram a lot because I think it does a good job of explaining some of these factors. So when you think about our roofs, the radiation, the solar radiation will hit the roof and some will be reflected off. Some will be absorbed and through conductance will come into the interior of the building. But within that material, some of that energy will also be emitted back out to the atmosphere. And I don't have it in a slide here, but I'm just going to bring up a radiant barrier is a building product. The textbook talked about them. We can go into a little bit more on Friday. But a radiant barrier is a highly metallic, a shiny thin layer, maybe a 32nd of an inch, that in certain circumstances in your roof assembly, if you install it in your assembly, it will help less conductance of radiation coming through the material and will increase the admittance back to the atmosphere. And typically they're made out of some type of polymer, including a lot of aluminum in there, because it's going for a very shiny effect, that radiation is hitting that shiny metal layer and reflecting back out. The one thing that is important for a radiant barrier assembly, though, is you have to have an air gap on the interior side of it. Oops, so tiny circle. You have to have an air gap here, because otherwise what happens is that sunlight's gonna, or the energy, the radiation's gonna hit that barrier, and if it's directly attached to its surface, that energy is just going to go straight through via conductance if you don't have a small gap. And the industry standard is about an inch. It doesn't have to be very big, but if you can't get that air gap in there, there's no point in putting it in. And the reason I know this is there's another building product called a SIPS panel, which is a structurally insulated panel. Another one of these inventions to have better performing buildings, where they take a few pieces of plywood and in the factory put rigid insulation in between. So you get all these pre-manufactured plywood panels getting shipped out to your job site that then get put together as your walls. Instead of a stud wall construction, you have this panel construction. They can do a really great job. They give you a good performance. There's a lot of planning that has to go on to coordinate your electrical and mechanical, which typically gets installed in your walls. They're also a great roofing product because they go down really fast. They're high performing. However, if you're going to have a cathedral ceiling design on the inside, if this is, oops, where's it go? You're going to have your, I can't draw my circle very well. Undo. If you have a cathedral ceiling inside where it's going to be all open, and the underside of that SIPS panel is going to be visible with perhaps a finished material on top of it, and there's no air gap, there's no space to put in that radiant barrier. And that came up on a project. We were doing SIPS panels. We were doing a wood ceiling finish inside that was going to be directly attached to that SIPS panel. And the client really was insisting that we put in this radiant barrier because someone had told her that it really makes a difference in the performance of your building. Well, it does in the right place. But if you don't have that air gap, it's not going to work. So, this slide is about cool roofs, though. Okay, so we briefly touched about cool roofs the other day. The way the industry rates them, they came up with this solar reflectance index. It only applies to cool roofs. Just the way solar heat gain coefficient only applies to glazing. And it's how they try to compare apples to apples for different roofing products. So, oops, back to mouse. Here is a chart that's got some different performances of different types of roofing materials, comparing the albedo and its emittance and its solar reflectance. reflectance index. Sorry, a lot of vowels there. For if you compare white shingles to black shingles, the black absorbs a lot of heat, so not a particularly well-performing product. Red clay tile actually reflects a fair amount, which is interesting that reflects more than white asphalt shingles. But it's probably because asphalt shingles are made out of bitumen, and it's just, I think it just, it's the granular surface, your white roof tiles are always going to be like this salt and pepper and kind of gray look, so they're not reflecting an awful lot. And they're also, if you guys have ever felt an asphalt shingle, the surface is very rough, and so there's a lot of surface area on there, so that's going to affect the amount of reflectance also. So if you were to think of like aluminum, here we go, here's aluminum, very, very shiny, very smooth. It has a very high albedo rating and a high solar reflectance index. One of, did they have TPO on here? Aluminum, right. White EPDM. It's not exactly a TPO roof, but this is a very high performing roof product. Oh, this is probably the TEPDM, is the T stands for thermo blah 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 something or whatever. It's one of the highest performing roof products out there. It's some sort of polymer, not exactly a natural product, but if you have a really big flat building with a very large roof surface, it's worth it for you. Typically it's worth it in a high cooling condition where you have a high cooling load, to put on a really highly reflective roof, so to keep your cooling load on your building down. This is kind of important to realize here, that reflectance is just referring to the visible spectrum of light versus the albedo, which is the full spectrum. So that gets into the other layers of light wavelength, like UV and X-ray and all those other things, wavelengths that are not visible to the human eye. And again, emittance, keep this in mind. Emittance is when the radiation hits a surface, and instead of being conducted through, it gets re-radiated out back to the atmosphere. Okay. How are we doing on time? Not too bad. Guys have any questions before we hit up the last few slides?
Nope.
Yep.
Nope, not at all. Pretty straightforward.
I'm sorry, what?
I said it's pretty straightforward. No questions.
Oh, okay. All right. Again, I can't see who's talking because you guys are all in this little strip. And anyway. Okay, so one of those other definitions from the beginning of today was solar heat gain. This is talking about the heat load that is hitting a building surface, typically the roof. It also hits our walls too. But solar heat gain is a combination of the direct solar radiation that's coming directly from the sun, as well as the diffuse solar radiation that is being scattered throughout the atmosphere. And don't discount possible solar radiation that's being reflected to your building. We're just talking about this with the Disney Concert Hall.
Yeah.
Okay, so we talked about our solar heat gain coefficient, but it's important to understand all the different types of heat gain that's coming through your glazing surfaces. So you're going to get some conduction that is going to come straight through. And that is going to be that's going to be dependent on the temperature differential between the outdoor and the indoor. Remember, everything's always trying to reach equilibrium. So if the inside is hotter than the outside and you get the solar heat gain, it's not going to conduct through the glass material. You get your radiation. That's what comes directly through the glass. And so those are those are the two types of heat transfer that affect our windows. The third, heat transfer, convection, doesn't apply to glazing. This is a good little diagram of what's happening here. So we have our solar radiation coming from the sun that hits, this is single pane glass. Some light is, or some energy, heat gain is directly transmitted through the glass, and that's going to be dependent on our SHGC. Some heat gain is going to be absorbed by the glass, and then for what is absorbed by the glass, it's either going to migrate towards the inside or migrate towards the outside, dependent on what the temperatures are on either side. And some of that solar radiation is also going to be reflected. Again, this is going to be a factor of your solar heat gain, and if you're looking at having like a low E coating or something in your glazing. We'll talk about low E coatings later. We're not going to get into that today. So at one point earlier, it came up the angle of incidence. That's how you measure, that measurement is from an assumed 0 ground plane to the angle of the solar, the sun, which is what we did when we looked at our sun charts and calculated what the angle of the sun was. So we've got conduction and radiation, and there's also reflectance, but that's not a method of heat transfer. Conductance and radiation are heat transfer. Convection, okay, so then so our other two, okay, so we just talked about solar heat gain, which is the solar direct plus the diffuse solar radiation. We also have our solar heat gain factor. That's going to be that solar heat gain, but the factor is per your square foot area, the surface area that is hitting your building. The shading coefficient, this is used to be part of the manufacturer's data. However, the SHGC has now replaced that. It took into effect what that angle of incidence is, what that sun angle is, and how much radiation would go straight through the glass. But these days, our glazing is so sophisticated with all of our insulated glass panels and our coatings and perhaps our argon or the color of our glass, It's been outdated because just calculating the angle for single pane glazing, we can't install single pane glazing anymore anyway. So it's just an outdated term. But if you come across it, the shading coefficient, it's basically just that angle, because at the different angles, different amount of radiation is going to go through that 1/8 inch piece of glass based on how much is being reflected and how much is being transmitted through. Okay, so we looked at this. And then the last factor today that we're gonna touch on is called the thermal lag factor. And this is important because when we get into looking at passive heating systems, this is why passive heating works. Lots of why radiant heating systems have a lag factor in terms of how long they take to heat up a space. So the thermal lag is the amount of time that it's going to take for heat to transfer from one side of the material to the other, or from one side of your assembly to the other side. And that's going to be based on how thick, or what that thickness of your material is, and on what the temperature differentials are on either side of that material. So for passive heating in the winter in cold environments, we're trying to keep your inside warm, so let's say 72 degrees, and the outside could be 50 degrees. So there's a big temperature differential. And okay, that's passive heating, which I don't really want to get into now. But it's basically the radiation hitting a surface and being absorbed by it, and then it's how long it takes for that heat to re-radiate out of that material back into the space. And does it come back into the space, or does it go back to the exterior? There's a bunch of different ways it can happen. It's all going to come together in your design when we're looking at passive heating systems. I just wanted to introduce it to the concept to you today as we're talking about how heat and solar radiation is affecting our building envelope. The book has a pretty good description on this too. So we will be picking it back up here with a couple more concepts on Friday about how our building envelope works. And I think that's about it for today. Do you guys have any questions? Okay.
I don't have a question for the class, but could I stay after and talk to you for a minute?
Of course.
Okay.
No problem. And I've already put this lecture up on Moodle. I put the assignment up that's going to be due on Friday. That's based on our thermodynamic lectures from last week. I think it's pretty straightforward. You guys, if just reviewing the lecture material, you shouldn't have any problem figuring that out. And so check out the link to the recordings on the YouTube. And if you have any problems accessing those, let me know. I think that same link's going to work all semester because I'm going to keep uploading the videos to the same sites. As far as I know, I don't think that address is going to change. I think that's it. Okay, if you guys don't have any other questions, I will stay in chat, and I will see the rest of you on Friday.
Thanks. Bye.
I'm going to turn off the recording. I can figure it out.